Okay, what we're looking at in this video is a general introduction to projectiles and horizontally launched projectiles. And you've seen, either by the video I showed or by demonstration in class, or you will see if you haven't already, this phenomenon over there on the left, where an object is simply dropped, that's the one in red, and at the same exact time it's released, there's an object that is projected or shot out with a velocity just horizontally, meaning its launch angle is 0 degrees. And the phenomenon we notice when we see this happen, we observe it in class with the demo, hopefully, if it works properly, but also with the videos that I'll show of it done with much more precise equipment, then we see both objects hit the ground at the same time. So this is a stroboscopic picture, like they're taking, say, a frame every 0.05 seconds or something like that, as if there's a strobe light. And you can see that each picture shows the balls at the same vertical position. So the red one is simply falling vertically. We would know how to deal with that already. That's just free fall. So this guy is just like an object dropped from rest and accelerating at little g. Its acceleration is little g. And there it goes. It falls. And this is like the dot diagram. You see the dots getting, or the ball, the red one, getting further and further apart in its position. So that's indicating a speeding up. Right? But the yellow one also has the same thing happening. If we were to draw the yellow one's position, but just in a straight line, it lines up with the red one. So it's also experiencing an acceleration of little g because it's lining up with wherever the red ball is. But the yellow ball is also moving this way. It moves over to the right horizontally each time. And so we have, in this case, a projectile for the yellow ball, whereas the red ball is just dropped from rest and free fall. All right, so we need a way to kind of compare those two things, and there are 2 points that we take into consideration after we notice this phenomenon. One, so this is true for all the projectiles we are going to encounter. Let's say 1. The vertical acceleration is little g. That's true for all the projectiles we deal with, whether they're projected horizontally or if you launch them up at an angle, if you launch them off a cliff with a down angle, the vertical acceleration is little g. Okay, so one way we might state that is the acceleration, which is a vector, in the y direction is equal to g for all projectiles. All right, that's convenient because we've already used little g for free fall. And this projectiles are in free fall. So that's another thing we could add. The vertical part, let's say the vertical part of projectile motion, no matter what type of projectile it is, but the vertical part of projectile motion is simply free fall. Okay, no problem. We've dealt with free fall. And we can see that in the picture and in the demonstration of the object dropped and the object shot at the same time because they're going to hit the ground at the same time. That's something that we noticed. They're hitting the ground at the same time. That's just like the Galileo experiment that we replicated with the thought experiment, and then we showed in the huge vacuum chamber in the YouTube video. Both objects in the presence of a vacuum, only gravity acting on them, hit the ground at the same time. Same for the projectile. All right, so the vertical portion of its motion, or vertical part of its motion, is free fall, and acceleration is little g. Okay, the second thing that we can say about for the projectiles we'll encounter, all of them, until I throw like a curveball in the practice problems later on, is that the horizontal acceleration of the projectile is 0. Okay, so let's look at the horizontal movement of the yellow ball over here. I'll make it in pink. So it moves like this far, then it moves this far, then it moves this far, then it moves this far. It's moving the same horizontal distance for each time interval. So that means that it's dots, essentially. Dot, dot. If I just draw it in a straight line up here, dot, dot. That wasn't very good. Dot, 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 dot. Horizontally, they're going to be equally spaced dots, which means what? If the dot diagram has equally spaced dots, what does that say to you about its speed? Constant, right? So that's constant horizontal speed. Meanwhile, vertically, we've got longer, slightly longer distances each time, and that's because we know we have little g, we have an acceleration. So the acceleration in the y direction is little g. The acceleration in the x direction is 0. So we're assuming no air resistance, so we're not going to have any force horizontally. Gravity is only a force vertically from the perspective of our ball or our projectile. It's just in the y direction. All right, so these are the two most important things. Vertical acceleration for our projectiles is little g. So that motion is just free fall. The horizontal acceleration is 0. So what else could we say about that? Horizontal speed is constant. Or you could say horizontal velocity is constant too. All right, so when we see both these things together, the big thing that comes from analyzing first this phenomenon over here, but also recognizing that the vertical parts and the horizontal parts have one acceleration and the other one has an acceleration of 0, little g and 0, we say that when analyzing our projectile or two-dimensional motion, we must analyze the motions separately. The horizontal and vertical motions we analyze separately. That is the whole essential beginning point for doing anything right with projectiles. And Galileo was the first one to do it, and it blew everybody out of the water because everybody else trying to figure out how you look at this parabolic curve without breaking it up into two different problems, one about the horizontal part in pink and one about the vertical part in green. So we analyze horizontal and vertical stuff. Let's not say stuff. Analyze horizontal and vertical parts of motion separately. That is the key. Separately. And then you can put them back together because it is one true kind of parabolic curved motion for our projectiles. But we look at what's happening in the x direction. That's horizontal. Look at what's happening in x direction. Separately from B, what's happening in the y direction. Let's look at what's happening in y direction. Okay, so based on what we said in numbers 1 and 2 up here, 1, the vertical acceleration is little g, so what's happening in the y direction? That's going to be free fall, acceleration little g. All right, so that's stuff we know. Part A of number 3 here, look at what's happening in the x direction. Well, look at number 2, the horizontal acceleration is 0, so this is going to be constant speed in the horizontal direction, or constant velocity. X direction, and we can say A sub x is 0. That's an A for acceleration with an x to tell you I'm talking about in the x direction is 0. And you'll see in the guided notes I had a table of the kinematic quantities and the kinematic equations, and that separated into horizontal and vertical stuff. And making tables is helpful to organize what you know about the projectile, because you want to keep the stuff you know about the horizontal or x direction separate from what you know about the vertical or the y direction. You've got to keep them separate, analyze them separately, and then put them back together at the end. So let's look at this example of just a horizontally launched projectile. All right, so let's see if I can make a, I don't know, like a table or something for this thing to launch off of. How about the color shape. Get out of ink to shape. Black shape. Rectangle. All right, so there's a table, you know, a desk or something. I'll draw the ground here, so that's obvious. That is, and there's the ground. That's the table. I want the table. Ground. There's the ground. Cool. All right, and let's. Oh, I don't have the Nerf gun. Oh no. Well, let's just draw. Let's just draw a little Nerf gun here. It's going to be inside the table, but the chamber is going to be right here, so that the dart can leave this way. All right, so there's like the launch velocity of the Nerf gun. Okay, so this is an example of a horizontally launched projectile. It's horizontally launched. It's one of the simplest cases we can talk about, and that means its launch angle, let's call it theta, is 0 degrees. All right, so it's in the direction of the positive x-axis. 180 degrees would be just as fine. That would be firing it in the complete opposite direction. All right, so we fire it with some velocity here. Now you got to ask yourself, okay, if it's at 0 degrees, is this in the x direction, the y direction, or a little bit of both? Is it a diagonal? Well, it's in the x direction entirely. Yeah, I mean, it's parallel to the x-axis. So this velocity here, let's call it velocity initial. That's going to be the speed with which the Nerf dart leaves the Nerf gun. And so in our case for the horizontally launched projectile, the initial velocity is the initial velocity in the x direction. That's all of it. There is no vertical velocity. So the initial velocity, let's say right here, let's say therefore the initial velocity in the y direction is 0. It's as if you've dropped it from rest. It's just like this picture up here for the yellow ball. This yellow ball has an initial velocity in the y direction equal to 0. Just like the red one. The red one has an initial velocity in the y direction equal to 0. They're being dropped from rest. But the yellow one does have an initial velocity in the x direction, and that velocity is how quickly it's shot by that little piston that shoots out. In the case of our Nerf launcher, it's how quickly does the Nerf dart leave the gun. That's what the pink is, VIX, initial velocity in the x direction. Okay, so here are two things that we know. We also already know that the acceleration in the x direction is equal to what? Yeah, 0. You might want to remember that. We don't have any air drag. Doesn't have like a parachute or retro rockets attached to it. It's flying through the air. And we know that the acceleration in the y direction is what? Yeah, good. I hear you all saying it. Little g. Every student who's watching my videos, which I'm sure is everybody. Okay, so we've got a couple pieces of information there about our horizontal and vertical motion. If I were to ask, what's the final velocity in the x direction? That should be immediate. If acceleration is 0, the velocities are the same throughout its entire flight. So its initial and any arbitrary final velocity before it hits the ground. Don't make the mistake of saying the final velocity is after it impacts the ground. That's different. There are a bunch of forces acting on it there. But its final velocity at any point in the trajectory is going to be equal to the initial velocity in the x direction because there's 0 acceleration. What other values do we have? Time, I don't know. And then we have delta x. Well, that's something we can find out, and we will need to find out because we're going to predict landing points. In the y direction, what else do we have? Initial velocity in the y is 0. That's not green. Final velocity in the y, we know it's not going to be the same as the initial velocity because little g is an acceleration making it speed up or slow down depending on where we shoot it. In this case, we know it's going to speed up downward because we're shooting it horizontally. So we don't know what v final in the y is. T, we don't know. Delta y, we don't know. So those are the things we're always starting off with. The non-question marks, the things we know, we're always starting off with that as known stuff for a horizontally launched projectile. This is a special case where it's launched horizontally, therefore its entire initial velocity is horizontal in its direction at 0 degrees, and its initial velocity in the y direction is 0. You got to have that if you're talking about a horizontally launched projectile. All right, now I'm going to try hopefully not unsuccessfully, to draw the trajectory of this thing, which should be parabolic. Trajectory is the path the projectile travels on, and for us it is always parabolic. Oh, already messed up. Come on. Nope, that's not good enough. Let's try zooming in a little bit. Don't mess up. Hey! Not bad. Okay. Let's say we mark where our projectile is. I'm going to erase this delta x because it's kind of in my way. Go away. Go away. Okay. Let's say we mark the position of the Nerf dart or the ball or whatever is being shot at a few different points as it's falling or being projected. I don't know, these may or may not, these probably won't be equal intervals based on the scaling, but I'm just trying to show different positions. All right, so this is throughout time, it's at those different positions. Now I'm going to draw some vectors. I know, one vector I know immediately is little g is always pointing down. Always, whether you shoot the thing up, down, sideways, at an angle, little g always points down. That's the direction gravity is accelerating you and everything else, towards the center of the Earth. And let's call, in this case, up the positive direction and down the negative direction. So that means g is going to be, for our problem solving, minus 10, or 9.8 if we're in the lab, meters per second squared. Okay, so that light blue vector, that's the acceleration vector. I'm going to draw velocity vectors on each black dot representing the position of the projectile. So in pink, the initial velocity is there in pink, right there. Okay, and we said it stays the same because the acceleration is 0. We're assuming no air resistance, and it's got no rockets on it, so that means its velocity in the x direction stays the same. So I would draw the same length, and I'll do my best, the same length horizontal velocity for the entire trip. It does not change because its acceleration is 0. So all of those are equal in magnitude. And I can just call all of them v sub x, because v sub x, initial, final, it doesn't change. That last one looks pretty bad, but you know it's supposed to be parallel to the x-axis. It's horizontal. Now, in green, let's draw what our velocity vectors in green vertically look like. Well, at the very beginning, the initial velocity in the y direction is 0 because it's all the velocity is just horizontal. Okay, so after some time, this thing has been, now that it's left the chamber, gravity's pulling it down, it has a little g as an acceleration, so it's got a little bit of velocity in the y direction. And a little more time goes on, and just like when you drop an object from rest, it's speeding up, so now Vy is a little larger. The length of the vector represents its magnitude, so there it's getting larger, larger still. Every second that passes, its velocity in the y direction is increasing in magnitude by 10 meters per second. That's happening every second. This one's even larger. And this one you might call V final because it's right as it's hitting the ground in my picture. There's V final. Okay, so the horizontal stuff is staying the same. The vertical stuff is increasing in magnitude because it's accelerating downward. All right, let's look at how we might figure out these unknowns, the question marks in there. And this, I also had a delta x here. I rewrite it now to remind us it's there. Or you know what, let's just, yeah, we can keep that there. That's fine. That's fine. All right, so let's draw in a couple of these unknowns. Use this guy. That's fine. All right, so let's look for the total journey of this projectile. What is its delta x? That's a horizontal displacement. That's what delta x is. How is its position changed horizontally? So I just care about the x values. So it started here. I mean, it started way up here at the top. But horizontally speaking, it doesn't matter whether I mark it up here or down here. I just care about its horizontal change in position. Right? So let me draw an actual arrow. There's the horizontal displacement vector right there. So that is not straight enough for me, but that looks better. So that's delta x. Okay, how about, and it's in the positive direction if I call right positive. Got to do that too. Let me add that to my thing up here. To the right is positive, sorry, to the left is negative. Always good to define that. Convention is to the right is positive and up is positive, but whatever. All right, now let's look at our vertical stuff. Let's use a darker green. And the vertical displacement, well, it's starting up here at the top, and it's ending down here vertically. So if I go to use an arrow to pick my displacement vertically, it's going to be from here. Oh, not right on top, because then we won't be able to see it. Let's just say it's right here so I can get it out of the way. What are you snapping to? Okay. All the way. Oh my gosh. All the way to the... Stop it. It's trying to be smart. Okay. So there's the vertical displacement. That's our delta y. Beginning to end point. Notice I got the arrows there. I'm not just drawing the height. I'm actually putting arrows there to show that it's a displacement vector. So just stuff is happening in the x and y. Purple and pink, that's x direction stuff. Pink's the horizontal velocity, vx. It's staying constant the whole time. Delta x is how far the thing has moved horizontally. And then the light green is the vertical velocity, which is increasing in magnitude because of little g, but it's always pointing downward. And then delta y is how far it's been displaced or how far it's traveled in the y direction, which is all downward. So delta y is going to be some negative value in meters. Delta x is going to be some positive value in meters. All right, how might we determine what these things are? Well, we have kinematic equations already. And if we start with delta, let's start with delta x, because that's what I had drawn first. I know delta x is, well, that would be initial velocity in the x direction. Now we need an additional subscript, because we got it's not just initial velocity, it's vix. In this case, because it's horizontal, the initial velocity is the velocity in the x direction. They're one and the same, because it's horizontally launched. But that won't always be the case for other types of projectiles. So the initial velocity in the x direction times time plus 1/2 acceleration in the x direction times time squared. Same exact kinematic equation we've had already. But what's up with acceleration in the x direction? What is it? It's 0. So delta x for our horizontally launched projectile and all projectiles for us, because acceleration in the x direction is always going to be 0. Bix times t. So there's the displacement in the x direction. It's whatever the horizontal velocity is times time. Cool. All right, let's see what we can say about the vertical displacement. We have, I'll use the same equation, except it's initial velocity in the y direction times time. We're calling down negative, so I'm going to write minus 1/2 gt squared. Right? You could write plus 1/2 gt squared, but you'd have to remember to make g negative 10 when you substitute it in there. I'm already taking care of the negative. This negative is that negative, because I don't like writing plus then a negative number. It's just redundant to me. Okay, so there's the quadratic kinematic equation in green for delta y. But for our horizontal projectile, VIY is equal to what? 0, just like it's being dropped from rest. It has no initial vertical component of its velocity. It's not being shot up at an angle. It's not being shot up straight up or straight down. So that's 0. Therefore, we have delta y, change of position, is 0 minus, so it's just minus 1/2 gt squared. So that's the same exact thing for free fall problems. Right? So here in this case, we would need to know the time, and we could say how far it's displaced vertically, delta y. As long as you get the time, you can say how far the thing falls. For our horizontal velocity, or horizontal displacement rather, all we need is the horizontal velocity and the time. So those are two things that are really important that we can look at for this. How about our final velocity in the y direction? I'd called this v final, I noticed now before what I need to make sure is that that's a y, because but the green is clearly indicating this is the vertical component. If I wanted to find v final in the y direction, I might use this one, v initial in the y direction, squared minus, because I'm calling down negative, 2g delta y. Okay, and but viy is 0, therefore v final in the y direction squared is minus 2g delta y. Okay, so that's one thing I could look at to find out whatever the final velocity in the y direction is. As long as I know the displacement and I have little g all the time, I can figure out how fast its vertical component of its velocity is. Mind you that at all of these positions I have drawn, it's not, the velocity isn't just what's vertical and what's horizontal. Its total velocity is the combination of both. So I'm going to draw one way to see this is to see the diagonal of this parallelogram. This is be adding the vectors. So if I added this one and this one, they're tail, arrow, tail, arrow. That's how I'm properly supposed to add them, but you are allowed to do it other ways. So I'm going to use, I guess, gray as a resultant vector here. So the total velocity here is this guy. That's the total velocity at that position, v. Okay, for this guy next to it, I can complete the parallelogram. And you get the visual of it as the diagonal is, I think, pretty easy to see. The same sort of thing happens when you're thinking about two people pulling on something in different directions. The resulting force is, or the way the object's going to move is going to be along this diagonal. But let's do this for each one. The total velocity should be increasing because I have a velocity in the y direction that is always increasing. And if you draw the vectors properly, then the velocity should be tangent to the parabola, though I've clearly not drawn everything to scale. But that's okay. That's not the most beautiful one there. There's the total velocity. And then this last guy, where's the velocity going to be the greatest? Well, right before impact, because gravity's been speeding the thing up the whole time. It's actually the best one. Okay, so now you can see in pink all the horizontal velocities staying constant. In green, all the vertical velocities increasing in relation to little g. They're getting bigger by an amount of 10 meters per second downward every second. And then in gray is the total velocity, x and y combined, which you can use Pythagorean theorem to get this value. To get the total velocity, use Pythagorean theorem to get that. Boom, which you already know how to do, because it's triangle. Split a rectangle in half, you get triangles. That's what we got here, parallelograms, and we've got Vx, Vy. Okay, so we've talked about how to get each displacement. We've talked about visualizing those vectors. Let's see what else we can do. Let's say I wanted to find time, and I'm going to take this equation, come down here. I know this is valid for my horizontally launched projectile because it has a 0 initial velocity in the y direction. All right, so let's say I wanted to find time. Now, this delta y is the displacement in the negative direction or the positive direction. We're starting up here, and down is negative direction. So is delta y going to be a negative number or a positive number? Negative number. Yeah. Okay, so notice there's a negative right here in front of my 1/2 gt squared, so that's the minus for g. And I also have a minus for my displacement vertically. So those minuses will cancel out once you put the actual change in position numbers in there. So this will become the same as that if I make them both positive. This is the same effect as if calling down the positive direction. All right, so let's say I don't know time, but let's say I do know the displacement, and I always know little g. So as long as I know the height of like the table it's being launched off of, then I know how long it takes to hit the ground. All I need is the height. So I can solve this for t. I have twice delta y, the height of my table, divided by little g equals t squared. So I gotta root it. There's t. Call this one fall time for horizontally launched projectile. There you go. And if delta y is like the height of your table, so you're going to launch stuff off a table. So it's going to be square root twice the height of the table over little g. That's how long it's going to take to hit the ground, assuming you measure it, the height properly. Okay, how about in purple, our horizontal stuff? Let's say I wanted to find the time. Well, from this guy, I know this is going to be true for all of my projectiles, not just horizontal ones. If I wanted to find time, then I have delta x over the velocity in the x direction, which I don't even need the I in there because it's always the same velocity because there's no acceleration. That equals t. So distance over speed is time is basically all we're going for here. The same thing you could say about the initial horizontal velocity. So here's one for time that's useful with the horizontal stuff. Let's say we came over here and we wanted to know vi in the x direction. What's that? Well, rearranging that equation, we've got delta x over t equals vix. So if you know the range, the horizontal displacement is frequently called the range. So let's also make a note of that. This horizontal displacement, delta x, is, that's nasty. Delta x is also range. Okay, so if you know the range, how far away from the base of the table the Nerf dart landed, that would be delta x, and you knew how long it takes to hit the ground, that would be t, then you would know how quickly it left the dart gun. You would know its initial velocity in the x direction, which in the case of the horizontal projectile is its total initial velocity, is its velocity in the x direction, because it's not changing, because we said acceleration is 0 in the x direction. Blah. Okay, so this is true for all projectiles, these guys that we have here in purple, because the acceleration in the x direction is 0. Notice here's a t, right? And here's a t over there. So the t's can be substituted back and forth between the horizontal and vertical stuff, because the object isn't splitting into two different things that have two positions at two different times. It's just one object in the same time. So if you know the fall time is square root twice the height, or twice delta y over little g, you can substitute that in over here to help you figure out either the launch velocity horizontally, or maybe it's delta x if you wanted. This t could also go up here, right? Okay, so we've looked at how we might find displacements vertically, how we might find time. Let's see one other thing over here. We're talking about final velocity, or velocity at any point in time. We had, what other equations could we possibly use? I mean, we could look at delta y. You just got to be careful with this one. You know you have an acceleration here, so viy plus v final y times t. So if you have t and initial velocity is 0, then you just have 1/2 times v final y times t, or twice delta y over t should be our final velocity in the y direction. So one approach you could use to also figure out your final velocity in the y direction. Here was one from our vf squared equals vi squared equation. Here's another one. And then how else could we approach that? We have our original equation, v final y equals v initial y. We'll call it minus gt because we've been calling down minus. Initial velocity is 0, right, in the y direction. Therefore, we'd have v final y is minus gt, which we've used all of these before already in just regular free fall stuff. So there's 3 different ways to look at final velocity. I would need to square root that first one. Obviously, this is still v final squared, and if you square a negative velocity, like this velocity at the very end is in the negative direction because it's pointing downward, if you square that, you get a positive value. So you have to be careful. You have to think about, what is my direction? Am I calling down negative? Then the final, every velocity in the y direction is going to be a negative velocity. It's telling you direction with the pluses and the minuses. Okay, how long have we been going for? Probably too long. All right, so let's recap real quick. We've looked at the 3 most important things about projectiles. 1, the vertical stuff and the horizontal stuff need to be kept separate and analyzed separately. The vertical acceleration is always little g, so it's free fall in the vertical part of motion. The horizontal acceleration is 0, so it's just constant velocity motion. And then part 3 is when I restated analyze horizontal and vertical parts of motion separately. And you can we always want to draw a picture for projectiles. We don't always need to draw in the vectors as I've done, though it's very important to recognize that these vectors are representing the real components or parts of the thing's true total velocity, which was denoted as regular v and drawn in gray. That is always the particle's true total velocity, but we need the component parts because we can only look at the vertical stuff by itself, horizontal stuff by itself, and then if you want to know the true v final, you figure out vx, you figure out vy final, and then you Pythagorean theorem that thing. Also, if you know their values, you can determine either this angle, call it theta, well, that's what I call the launch angle, so call that one alpha, or you could determine this angle, call it beta, and that's how you could describe maybe at what angle it impacts the ground or something like that. But that's just the basic trig stuff we've already started to practice with vectors. We've looked at some of the most important things. This is just for horizontally launched projectiles. So you notice that the launch angle here is 0, and that means not only is this true, this is always true, I just boxed ax equals 0, that's always true for projectiles. Not only is this, this one in, I'm running out of colors here. Let's use whatever this is. Okay, so this is true always for horizontal projectiles. The velocity in the x direction always stays the same for projectiles because it's got that 0 acceleration. But specifically for horizontal projectiles, all of its initial velocity is vx because it's got no vertical stuff happening. All right. For horizontal projectiles, this is true. The initial velocity in the y direction is 0. For all projectiles, the acceleration in the y is g. All right, so those are some specific things about horizontally launched ones. And we showed how to find different values like displacement or looking for time or a final velocity in the y direction. We'll have some problems that start with just horizontally launched projectiles, and we'll have a couple more videos, one on surface-to-surface launch, one on non-surface-to-surface launch, and a couple on solutions to practice problems before we do the kind of full list of assessment questions that will get posted hopefully by Thursday. So you'll know all the questions that the test might come from. All right, we need to end this now. Yeah, review that. Also know you can check in the book for extra practice questions and a little more information. That's all.